Good afternoon. My name is Christopher Karwowski. I'm with Chi-Tech Technologies Corporation based in Taiwan. I'm here today to give you a presentation on dialkyl hydroxyalamine, or what we call Daha. It's an antioxidant used for long-term heat stabilization. Dr. Chris Chu, the owner and president of our company, has put together this PowerPoint presentation, and I've been asked to give my input on it. What is Daha? Daha is an acronym for dialkyl hydroxylamine, which represents a family of molecules as shown below with a primary antioxidant functionality. You look at this, we call it the hawk. It looks like a bird of prey, and it actually is the ability to prevent yellowing and oxidation in your polymers and polyolefins. It's a very strong molecule. Dr. Chris Chu talked about this last year. It was called Revenox 420V, and we're bringing additional information in today's presentation. Thermal auto-oxidation, how it works, is explained here. Daha scavenges free radicals appeared in antioxidant pathways and work around here. Take over here some peroxyl radicals, some alkyl radicals, carbon-centered radicals, and this whole process is one big loop of exchanging radicals on the electrons. It's pretty cool stuff. Daha and three other types of primary antioxidants, long-term heat stabilization. First one is hindered phenolic. You can see it goes across long-term heat stabilization and melt process stabilizers, melt flow index. The next one is Daha. Operates at around 120, 260, 270 C. The third one is hindered amine stabilizers, HAS. Work being from 0 up to about 120. Oops, went the wrong way. And then lactones work from 150 all the way over up to 300. So you can kind of see the range of antioxidants and their primary heat source regions and how they work. Applications of Daha. Daha has been explored as a primary processing stabilizer for a few unique applications. Resistant to gas fading. And what do we mean by this? Is it doesn't change color. Your polymer stays the same color. Next one, low discoloration. Again, because you don't have the gas fading. Next one, low migration. This is very important. You don't want your antioxidant to leave your polymer or your application. So very low migration, the product's going to stay within the molecules of your polymers, your polyolefins, so it doesn't come out. It's very important that you have low or no migration if possible. And resistance to radiation, basically UV, ultraviolet radiation, UVA, UVB areas. What we have here is Daha is resistant to gas fading. We have an example here where there were 19 samples were put into an oven, and you can see that many of them have changed color. Daha has maintained its color from before and after the gas fading process in an oven. So what you see here is even after we've heated it up to its extreme, the Daha does not change color. So your polymers and your monomers and your applications will stay clean and bright and not have color discoloration. Daha versus hindered phenolic antioxidants on polypropylene. We've got some examples here. We've got some samples, 1, 2, and 3. First sample, we have Daha, 300 parts. We've got phosphite antioxidant. Everybody knows at 168. We don't have to talk about that. We have calcium stearate, DHT4V, which are kind of based on the chemistry of your polymers. And we also have the phenolic 1010. So we basically are comparing our products to all of the other phenolic and phosphate antioxidants. Test conditions, twin extruder, Coporian, ZSK 30, component temperature is 220 C, and the injection temperature was about 220 C as well. This is the HAS, the hindered amine stabilizer, the CAS number if you want to look it up. we show that the Daha is superior in color. In samples 1, which we had Daha and antioxidant 168, you can see how the color has helped. It's stayed below the delta Y. So -4 would be a little bit on the blue side. A plus number would be on the yellow side. The Daha and HALS, the hinderamine, that should be, Chris, that should be HAS. I must have missed it. I apologize. But this is HAS. And you see everything through 5 extrusion passes has stayed below 0. So we do not have here's the original color. So the original color is about 3.5. After 5 passes, you have a delta of maybe about 2 maximum, which is very, very good. So your color retention is very, very good. As you can see in this area here, we have reached nothing that has gone more yellow. You look at the 110, the 168, which is basically first generation antioxidants for polypropylene. And what you see here is kind of starts out the same color as everything else. But after the second pass, it starts going yellower and yellower and yellower and yellower. So from here, -2.5 to here 5, you have a delta Y of 7, which is very significant. You don't want to be seeing that type of application in your products, be changing from basically a pure white to a cream color. Not good. Next slide, we talk about the Daha comparison and melt flow index, MFI. What we have here is samples 1, 2, and 3. Again, Daha and 168, Daha and hinderamine stabilizers, and the first generation antioxidant. So you can see the melt flow index of the pellet at 0 pass. You can see melt flow pellet at the 3rd extrusion. So you can see that we have very good numbers with the Daha and HAS, the hinderamine stabilizer, to make sure your melt flow index stays coherent and protective, or not protective, but flows for your product. Another critical test is Daha under long-term heat aging, LTHA. We have polypropylene containing Daha, showed severe yellowing in long-term heat aging. That's number 1. And then 500 hours in oven at 131 C. In presence of HAS, the yellowing was not as severe. And then in 3, Daha and HALS is superior to the 110 and 168 for long-term heat aging. So what we have here is 110, 168 is number 3. Here's the heat aging. As you can see, the color change from a white to a slightly yellow cast. But you can see the first generation antioxidant has changed color dramatically over the 500 hours in an oven at 131 C. So what we're showing you here is how strong Daha and the hinderamine stabilizers are in keeping your product clean and bright and white. It's a pretty severe test at 500 hours at 131 C. Again, some more testing that's done in the industry is the fold breaking at 500 hours. First pass, second pass. First pass, Daha and 168, yes and yes. Daha and hinderamine stabilizers, no and yes. And then the old technology, no and yes. So the conclusion is polypropylene containing Daha became brittle with long-term heat age effect, and it has helped retard the development of this brittleness. So if I can't really go back because my mouse doesn't allow me to do that, but if you saw previously, you can see where the samples were brittle and broken. Hinderamine stabilizers help long-term heat aging irrespective of loading. And what we have here is the additional tests 5, 6, 7, 8, and 9. The levels of Daha from 200 to 600, or from 0 to 600. The amount of hinderamine from 0 to 600, and the conclusion is the Daha developed severe yellowing in the absence of hinderamine stabilizers on long-term heat age stability test. Daha did not develop severe yellowing with the presence of Has at lower dosages. So you can see by this generation of data, you can optimize at what point you need to be to have the right level of Daha and Has. Basically, it's about 50% Has hinderedamine to make it work. Hinderedamine stabilizers work for nitrone on LTHA. What we have here is the molecular structure of the Daha. A little bit of reaction going on here, making the nitrone down here. So the basic conclusion on tests 10, 11, and 12 is nitrone does not protect the melt flow index as well as Daha does, and nitrone causes severe degradations in the absence of hinderedamine stabilizers. So the focus on what we're talking about here is how important your hinderedamine stabilizer is in your polyolefin or your polypropylene products. Alkyoxyl HAS works on long-term heat aging even better. We all know what this product is. It's been out there for quite a long time by one of our competitors. Again, we have sample 1, sample 6, sample 7 that we looked at. The conclusion of this data and testing that was done is the alkyl Has was superior to plain hinderedamine stabilizers in color performance on long term. DHT4 was critical in the melt flow index, and the calcium stearate's role is not clear. So what we're still seeing is the ability of your hinderedamine stabilizer to provide you so much better color retention and prevent you from gassing, yellowing, gassing, and allowing your products to stay clean and bright. Here's the molecule. There's the CAS number. In this presentation, we can't really tell you the trademarks, but you're all very smart people, and I'm sure you know what it is. The hinderedamine stabilizer works on LTHA regardless of the Daha. So what we have here is test 1, 3, 4, 6, and 7. A little molecular structure here, some chemical reactions going on here, DBHA here. You can kind of all see how this all comes together. And we talked about the nitrous oxide, DBHA, the hinderedamine stabilizer 944, which is one of our products. You can see all of the information here. So we're showing some very good ability for the Has to do its job. Sulfur antioxidants cannot replace hinderedamine stabilizers. The sulfur antioxidants may be a little bit cheaper and may be used more frequently in the past, but the work that Chi-Tech has done has shown that the hinderedamine stabilizer still provides the best color and the best melt flow index and the best brittleness testing for your products. Here's the example of the yellow mechanism hypothesis. There's trace amounts of an unknown degradation catalyst. We're still working on this hypothesis, and we'll probably have some good results for you 6 months from now as to what these products are. Feel free to contact Chris or I to get that additional information as it becomes published. But what we have here are the Daha and the Has, where it's breaking down, what it breaks down to, nitroxyl, nitrone, and then the DC is a degradation catalyst. Deactivated DC, which was not able to cause polypropylene from turning yellow and brittle, and over here, activated degradation catalyst, which caused polypropylene from turning yellow and brittle under long-term heat age. Conclusions. Daha requires hinderedamine stabilizers for better color, brittleness, and melt flow performance for long-term heat age. The hinderedamine stabilizer to Daha ratio, remember I talked about it earlier in the other test that we did, are about 50%. So you have a 2-to-1 ratio or 1-to-2 ratio depending on which side of the math equation you're looking at. But basically, you need 50% of the Has to your Daha to give you the best performance for color and brittleness and melt flow. Alkyoxyl hinderedamine stabilizer is superior to regular hinderedamine stabilizers for long-term heat age. And secondary antioxidants don't help the long-term heat age of the Daha at all. And finally, as the previous slide show, trace amounts of unknown degradation catalyst hypothesized to be the cause of yellowing and brittleness, which was activated by nitrone, but deactivated by the HAS, the hindenamine stabilizers. So at this time, I want to thank Chris Chu and the team in Taiwan who put together all this test data and put together all the PowerPoint presentation. If there's any questions, I'll take your questions now. Thank you very much. Have a good day.